Right, so this is where we were last time. Um, let's see. My plan is to maybe go over, there were some things that I kind of skipped like this because I wanted to go through that third technique last time, so we can go over that, and we can also go over your questions on the homework that is essentially due this weekend. So again, it's not like the entire homework is due per se. We'll have this quiz where one of the problems from that homework will be assigned to you, and then you already have your homework ready, so you just take a picture and that's it. You'll only have 15 minutes to upload whatever problem is given to you, but you can open it at any time starting tomorrow. Okay, right, so let me go over this first, I think. So we had Euler's formula, vertices minus edges plus region or plus faces, depending on whether you're working on the plane or you're working with polyhedra, equals 2. So here, for each figure shown above, count the number of vertices, edges, and faces, and find the difference. So for all of them, it should give you 2. Do you have any questions there? Did you try some of those? I don't know, for instance, I don't know, this one right here, 1, 2, 3, 4, 5, 6. So V equals 6. And then we have the edges, 1, 2, 3, 4, 5, 6, 7, 8, 9. So edges is 9. And then we have the faces. We have this little triangle right there, like the bases. If you turn this 90 degrees, I guess, if you extend it, you have those 2 triangles, and then you have 3 rectangles around that lateral surface. So you have one on the back, one on the bottom, and then I guess this one right here. So like the one in front of us. So that's five faces. And so if you do D minus C plus F, that's 6 minus 9 plus 5. That should be a 2. Mm-hmm. Okay. So you can try and just double check that all of them are 2s. That's the H14. More interesting, I think, is H18, where they don't really give you a picture. You don't have to count. What you have to do is figure out something about the figure. So it says a dodecahedron has 12 faces and 20 vertices. So B equals 20, F equals 12. Each face has the same number of edges. So that means that the regional degrees are all the same. So R1 equals R2. And because there is 12 faces, then there are 12 regional degrees. That's just the number of vertices, or the number of edges in each face. Mm-hmm. So for example, the regional degrees in the cube, there are 6 regional degrees because there are 6 faces. All of them are the same because every face is a square, and a square has 4 sides. Mm-hmm. So in the dodecahedron, all the regional degrees are the same. We don't know what they are. We're not told what they are. if you're familiar with the dodecahedron, it's actually pentagons, so all of these are fives. But anyways, so this is the information that's given. 12 faces, 20 vertices. Each face has the same number of edges, so the original degrees are the same. Use the Euler's formula and the original degrees to determine that what that number must be, meaning this common R value. So number of edges we need to know. What we know is that twice the number of edges equals the sum of the regional degrees. And let's say we're looking for that common value R. So I'm just going to replace this by R. And so that means that this is 12R. So E equals 6R. Mm-hmm. So that's using the regional degree theorem. And then we use Euler's formula. You know that vertices minus edges plus faces equals 2. You know that vertices is 20. Edges, I'm going to replace by, well, actually, let's do, we need R, but we're going to find both E and R. So E plus faces is 12 equals 2. So 20 plus 12, 32 minus 2, 30. So E equals 30. And therefore, with this one, R equals 5. So the faces are pentagons. And there are 30 edges, 12 pentagons altogether, 20 versus, that's a dodecahedron. And then it says repeat this for the icosahedron. In the icosahedron, you have, is the dual of the dodecahedron. You'll see what I mean. So we have 12 vertices. We have the number of faces is 20. And in the icosahedron, we also have that all the regional degrees are the same. So all the faces are the same. In fact, they're congruent. They're exactly the same size and everything. So all of those are the same. I'm just going to call this common number R. And, we don't know what R is. We don't know what E is. But we can do the same thing. So 2E equals the sum of the Ri's. There's 20 of them. All of them are the same. They're equal to R. So this is 20R. So E equals 10R. And then we have vertices minus edges plus faces equals 2. Vertices there are 12 minus edges plus 20 faces equals 2. So this gives you that the number of edges. Did I do this? Yeah. The number of edges is 30 again. And therefore, from here, R equals 3. So the faces are triangles.
How do you know regional degrees are equal?
Oh, just because the icosahedron, the dodecahedron, they're talking about the solid, the platonic solids, and there's only 5. Those are the only regular polyhedron, meaning that all the faces are the same, and therefore all the regional degrees are equal. So not only the regional degrees, not only the faces are triangles, the faces are actually equilateral triangles, and the same thing here. So these are actually regular pentagons. Like this counting doesn't really tell you that, but and these are actually equilateral triangles. Now all the edges are the same length in those two polyhedra. All the faces are exactly equal. So let me just clarify here. All the faces have the same number of edges. And again, not only that, in the regular icosahedron, all the faces are exactly the same size and shape. Okay. And so, let's see, maybe we can do, where's my book? Oh no, I cannot find the phone. Oh, here's my book. So maybe, oh no, it's not this one. This is the combinatorics one. Here's the Catherine one. So I thought I could show you something else that you can do with this type of thing. And maybe actually we can go over the homework and see what problems are, which problems you can do. You can use things like this.
Like for problem 37, my question is, how do you approach it by trial and error?
Okay, wait. Let me go. We'll go over that. Give me a few minutes. All right. It was Elizabeth.
Yeah. Okay, no worries.
So give me a few minutes. Let me see. There's also something in the chat. Okay, so let me go over the chat first. So this is about the quiz that Plums assigned you. Yeah. So let me go in order. So first thing is, I had this in the slides from last time. Here are the problems. So the first page in the, just you can see this, right? Yeah. So the first page of the slides from last time, these are the problems that are assigned. We'll have quiz 7 due this weekend. So the idea is that you finish your homework, you have it ready, you open the quiz, it will give you one problem at random. I have nothing to do with it. So when you open it, the system will give you one of these 7 problems at random. You have 15 minutes to take a picture and upload it. So this is really a homework assignment, and I'm only grading one problem at random from everyone. Okay? So that's what I was talking about. And this information is in the slides, first page of the slides from last class. So does that clarify all the questions in the chat? Is there anything else about that? All right. So from these problems, 24, 25, 27, okay, from these problems, let me go where I was. So here, let's see. So in 27, you can do things like the ones we just did in the previous page, the ones we went over. So in 27, again, this is part of the homework. And also the problems, that those 7 problems are also in the model, one of the headings in the model, so that you can easily know what they are. It says let R be the number of regions in a plane diagram of a 3 regular connected graph. Okay, so R equals number of regions as usual in a plane diagram of a 3 regular connected planar graph. Okay, so you need to find E in terms of B, so number of edges in terms of the number of vertices. They didn't give you either, they only gave you the number of regions, right? And B, you have to find R in terms of B. So number of regions in terms of the number of vertices. So let's say they didn't tell you any number, right? So in fact, I could just say V, E, and R as usual. So vertex edges. A number of regions. Okay, so here, what can you use? What tools you have available? You have the degree theorem, the regional degree theorem, and Euler's formula. And essentially, that's all the theorems that you have available. The other things that you have to do is the information that they gave you. So it is connected. They're telling you that it's connected so that you can use the Euler's formula. That's really the reason why they're telling you it is connected. If it's not connected, then that too is not going to work. Okay, so that's the only reason. So if you want, you can kind of disregard that. Just say, okay, because it's connected, Euler's formula says this. 3 regular, they're telling you this so that you can use the degree theorem. Because the degree theorem tells you that the sum of the degrees, and in this case, we don't know how many vertices we have, but we want to give, they're asking us to give these, the values of E and R in terms of V. So all the degrees in this case, because the graph is regular, then all the degrees are 3. Okay, so you add all degrees. How many of those you have? V, right? Because you have V vertices. We don't know a number, but we call the number of vertices V. So you add 3 plus 3 plus 3 plus 3 for as many vertices as you have, and that gives you the number of edges. And then you use Euler's formula. You have Euler's formula is vertices minus edges plus regions equals 2. If you already have the edges in terms of V, then you can solve for R, and it's going to give you R in terms of V. So it should be pretty easy, but I don't want to do it for you. I just wanted to give you pointers. Right? So use the degree theorem for the first part, and then use Euler's formula combined with the first part to get the second part. So 24, 25, 27, 23. Okay, and also, since we're talking about Euler's formula, and not necessarily, most of the problems are show that this is planar or show that this is not planar, but these are different nature. That's why I kind of pulling them aside, since they're similar to what we were doing. So this one says a soccer ball has 32 faces, each of which is a regular pentagon. So what does that say in terms of our notation? So in our notation we have V, E, F, the regional degrees, the degrees, I guess. So if they're telling you that all the faces are regular pentagons, what are they telling you in terms of our notation?
Is R equal to 5?
Can you say that again? Sorry, I couldn't hear you. Let me turn on. Okay, go ahead.
I think something is equal to 5. I can't remember. When we stated it's a regular pentagon. I think E is equal to 5.
Let's see. Let me go back here.
All vertices are equal, right? Regular mean.
Regular pentagons. So what are we talking about? Are we talking about edges, vertices, or bases, or regions?
Vertices, right?
Regular pentagons? What's a pentagon?
Isn't it? We just did it.
Right? Pentagon is the face of the polyhedra, right? In the polyhedra, in any polyhedron, we have the corners. Those are the vertices. The edges, these lines, right? And like zero dimensional, one dimensional, and two dimensional, the faces. And they're saying regular pentagons. So they're telling you what kind of faces you have. Mm-hmm. Like here we have squares, right? That's that tells you what kind of face you have. And if they're telling you what kind of face you have, they're telling you how big it is, right? They're telling you the regional degree. So like in the cube, all the faces are squares. It means that the regional degrees are all 4. In my conclusions, when I got that all the regional degrees are 5, what I'm saying is that all the faces are pentagons. Not necessarily regular pentagons, but pentagons. And when I get to all the regional degrees are 3, and it's telling you something about the faces and telling you how big they are, what kind of shape they are. These are triangles. Mm-hmm. So when they told you that all the faces are regular pentagons, what I'm telling you is that R1, R2, R3, or regional degrees are 5. All of them. Mm-hmm. Then it says, because of the angles involved, exactly 3 faces meet at each corner. Okay, so that they're telling you how to glue, your polyhedron. If you go back to these pictures right here, you see, like for example, here, this one has 1, 2, 3, 4 faces that meet at the vertex. This one has the rectangle, the bottom rectangle, and the triangle. Three faces that come together at the vertex. They're giving you information about the vertex. What are they telling you? If I told you that there are 3 faces around this vertex, what am I telling you about the vertex? What is that 3 for that vertex?
There would be 3 vertices if face is 3.
If there are 3 faces, then that means that there are how many edges are attached to this vertex?
3.
3, as many as faces. 3. So they're actually giving me the degree of the vertex. That makes sense? Look at this one right here. This one right here. It has 4 triangles that come together at this point, right? And because the triangles share an edge, there's going to be exactly 4 edges attached to this vertex. So this is the degree of the vertex. Let's say this is V. The degree of V is 4. And this is the number of faces at the same time that come together at V. So they're actually giving you degrees of vertices. Same thing here. So this is degree, if I call this U, the degree of U is 3, and it's the number of faces that come together And it also works for plane diagrams, not only the number of regions that come together at the vertex is the degree. Mhm. So it works in the polyhedra, and it also works for plane drawings. So if I go back to that homework problem here, that's telling you that exactly 3 faces meet at each corner. So the translation is that the degrees of the vertices of all vertices, of each of the vertices is 3. Each vertex has a degree. And then it says, without looking at the ball, if you have a soccer ball, you can actually confirm your finding. Determine how many of each type of face there are. So in this one, not all the faces are the same shape. Mm-hmm. Wait. Which is it? Oh, sorry. I didn't read correctly. So it says all faces are regular pentagons or hexagons. Sorry, I didn't finish my sentence. And so regional degrees are 6 or 5. Some 6, some 5. Okay, so that's what the problem actually says. I didn't finish reading the sentences. And then they're asking you how many of each there are. Huh? So again, use the degree theorem, use Euler's formula, and use the regional degrees theorem. When you use the regional degrees theorem, as opposed to my other examples where every number is the same, here you have a sum of 5s and 6s, but it needs to give you a specific number. So there's going to be a unique number of 5s and 6s that will add up to twice the number of edges. You need to first find what's the number of edges so that you can find that unique combination of 5s and 6s that will give you twice E. Okay? So, but it's the same kind of trick. Degree theorem, regional degree theorem, and Euler's formula. Right? So I think those are the only 2. Let me just make sure. So 24, 25, and 29. Oh, 29 is one more that uses, it's this kind. So 29 says, let G be, again, these are not full solutions. These are, let me actually say hints. So that for the homework. So for H29, it says, let G be a connected planar graph with 3 or more vertices. Again, they're telling you that it's connected so that you can use Euler's formula. Connected and planar, right? With 3 or more vertices. Do you remember when we said something? When we say something about having 3 or more vertices? If I go back in my notes, you'll see we have that note. This note. Remember?
Yeah, greater than or equal to.
Exactly. Now we know that all the regional degrees are at least 3. Right? So when you read your problems, just be careful that every single thing that they are giving you is important. Many times we just, like, for example, I don't read that it says connected, and I'm thinking about that like a single polyhedron when I'm using Euler's formula, and I'm not thinking about the possibility of having 2 at the same time, which are actually like a disconnected graph. But the reason why this is here is because if I try to do this for 2 polygons together, then it's not going to give me 2. Okay, so when you read problem H29, when it tells you that there are at least 3 vertices, it's so that you can use this note. Okay. Here. So let B in and R as usual. Use the regional degrees in any plane diagram of G to show that R is less than or equal. Let me write it down.
So
Professor, just wondering about H27. What does it mean by find E in terms of V or find R in terms of V? Because if I use the Euler's theorem formula, isn't that impossible? Because in terms of V, doesn't that mean there can be no variables of E or R?
Yes, that's why you see from Euler's formula, I can say here, from Euler's formula, I could say V equals 2 plus, E. I could say E equals V plus R minus 2, but that wouldn't be okay because I still have the R. So that's why we're using all the other stuff so that we can somehow get rid of the R. Okay?
Do we solve for R or substitute R, but then you substitute R, you would just have another E, won't you?
No, you need to use something else. If you only use Euler's formula, you're not going to be able to do it. That's why we have all the other information, the degree.
Oh, okay.
Yeah. See? So somehow you need to rewrite R in terms of V. In terms of actually, it's going to be you will be able to replace it by only V's. It should be E equals something only in terms of V. Okay, so in H29, we want to show this first. And then, Elizabeth, do you still have a question? I didn't see that your hand was raised.
Oh, no, I'm just waiting to get on the last
one. Yeah. Okay, so we'll get to it. Don't worry. I just want to group my problems by type, right? And these three are kind of a similar type. So
yeah, no worries.
H29 asks you to prove two things. And actually, in this order, because A is going to be used for B. So actually do it in this order. So show that R is less than or equal to 2E over 3. And then prove that E is less than or equal to 3E minus 6. This is a very useful statement. I don't know why it's not usually given as a theorem, but this inequality is used all the time. So, so how can we do something like this? Same idea as with the others. In this problem, you can use the Euler's formula, definitely. So Euler's formula gives you V minus C plus R equals 2. You want to show that R is less than or equal to 2E plus over 3, because you have this 2E over here, right? You want to use the regional degree theorem or the degrees theorem. That's pointing, that's hinting that maybe we should use the degrees theorem or the regional degree theorem, because 2E equals sum of degrees or sum of regional degrees. And because we are trying to round R, then you want to use the regional degree theorem, because the regional degrees tell us something about the regions, right? So this is telling you, use the regional degree theorem. So now you have the sum of the RIs from I equals 1 to R equals 2, right? So what is 2E over 3? You really want 2E over 3. And how can you bound the RIs? You want to use the note to bound the RIs. Put everything together. You see the number of, how am I going to get the R involved? The number of terms here is R. You use your note, all your RIs, that note that I went to, all the RIs are greater than or equal to 3. Because there are at least 2 vertices. You're going to have to put together all these sentences. You have because the problem tells you that there are at least 3 vertices, then all the regional degrees are greater than or equal to 3. You attach this bound here, so you can replace each I by 3 to add up over all the regional degrees. You know how many there are of them, and it's almost done. Okay? So once you have that, you want to use this in here with Euler's formula. So for this one, we're not really using Euler's formula. We're going to use it for that part. And that's it. I mean, there isn't the work. I don't mean to say that it's completely done, but it's the same idea as for the most part. Anyways, so questions up to here. All the other problems now are actually just either showing that the diagram is plane, that the graph is planar or not. So up to here, any questions? Okay. So let's see the
I have
others.
a question on I just have a quick question on H36.
Yes. Yes.
It asks us to find a subgraph that is either K5, K33, or a subdivision of one of those. But as far as I can tell, for part A, the graph is planar, which means it's not going to have a subgraph that is any of those.
Yeah. That one is a typo of the book. Yeah.
Okay. So for that one, just write planar?
For that one, just write planar. You're absolutely right. So the first one is planar. All the others, you want to actually show that.
I figured out all the others. I was just confused about that one. Thank you.
No, with good reason. It shouldn't be like that. It's a typo. So the first one in H36 is planar. And not only that, it's already a plane drawing, right? So it's obviously planar. So it really shouldn't be there. I imagine that from one version of the book to the other, maybe the problem originally said determine whether or not, or something like that. I don't know. I need one to prove that that is a planar and that one is. Anyway, so that's a typing. Okay. Okay. So for all of the others, you have to prove or disprove planarity, right? So let me start. For the first one, I think it's a little bit easier because in all of those, all those drawings are not planar. In H24. So if there are more questions in H36, we'll go back to that, okay? But for now, H24, just draw the graph with no crossings. And you can just do it in any way you want, trial and error. If it gets too hard, like for some of them, I don't know, this graph is not there, obviously, but if I give you a graph like this, imagine that the vertices are, I was telling Elizabeth this morning, imagine that the vertices are tennis balls that are attached by rubber bands. And that's your graph. And essentially, you can just pull one of the rubber bands one of the tennis balls. You bring everything together because everything is attached, and you can just leave it in a different position, and it gives you a different drawing of the graph. So you can move the rubber bands. You can stretch the rubber bands to go in a different direction. So, for example, here you can take. Because I do have that crossing and I don't want to have crossings, then you can pull this line, stretch this rubber band so that it goes around, right? So that one, you can just, one of those diagonals can be stretched so that it goes around. it remains attached to the same tennis balls, I guess, to the same vertices, but you can continuously pull it until it kind of goes, makes a plain drawing. So I know that for some, I'm mentioning this because I heard from some of you, from several of you, there is this even, I don't know, maybe some of you are even afraid because we're mentioning isomorphic graphs and isomorphisms were hard. And, we have to deal with isomorphisms and planarity at the same time. So it seems like too overwhelming. What we mean by drawing a graph that's isomorphic is essentially this: you have the freedom to stretch the edges as if they were rubber bands. They just keep attached to the same vertices. And you also have the freedom to move the vertices wherever you want. But when you move a vertex, it kind of pulls all of its rubber bands, all the rubber bands that are attached to it. So all the edges kind of go with that vertex when you move it. Okay, so for instance, for the first graph that you have right there, we have something like this. Actually, you know what? Instead of solving the homework for you, we can go back to one of the problems that we had at the beginning. Where is it? I know. It's over here. Yeah. So this one's. You see? So this is like H24. I think we did the first one but again, for this one, for something like this, you can try pulling out some of those edges. You can try to pull out like this one right here. You can bring it, stretch it. Think about it as a rubber band. Stretch it so that it can go around. Or this one. And let's see. In this one, I could one of these two diagonals needs to go out. So let's see.
Can we use Hamilton?
Yeah. So my point for H24 is that you can always use that Hamiltonian Hamiltonian circuit technique, but in this one you actually already have a Hamiltonian, like a very clear Hamiltonian circuit, right? So this one. And then all the edges that you're missing, just by just adding one by one. You don't lose generality if you add them in a certain order. All your moves are going to be forced. So here we go. So there's my Hamiltonian circuit. I'm going to label this and see which edges I'm missing. So I'm going to list them AD, AE, BV, BF, CE, and CF. And that's it. So I'm missing those 6 edges. Okay? Oh, by the way, so this is another one of those problems that if you're showing that it is planar, the order in which you add them, whatever you do, doesn't really matter as long as you show me a plane drawing. Okay? But if you're using the Hamiltonian circuit technique to prove that it's not planar, you need to give me the order in which you added the lines. Okay? In the exam, if you already check it, in exam 2, I already finished grading, it's there. You can go check my comments. I actually, because most of you didn't give me the order of the edges, if you notice, I actually tried to order, guess the order in which you added the vertices and gave you the points, unless I couldn't really find any way to order those vertices. But in general, I gave the benefit of the doubt to everyone. But in this one, please tell me, okay, if you're using this to show that there is no plain drawing, you need to tell me in which order you added the edges. If it happens to be plain, don't worry about it. Just a picture is enough. Okay? So I'm going to start by adding a V. I know this is plainer, so I don't really need to number them, but I will so that you know in which order I added them. It doesn't matter if it's inside or outside. I'm not losing any generality. And then I'm going to look at, so that I force my moves, my moves, I'm going to look at one that actually will cross this one if I were to draw it inside. Okay, so for example, AE, it could be inside, outside. And if I assume that's in one of those places, I will lose generality. So I'm going to skip that one. BV, same thing. You know, I don't force any crossing, so I have two possibilities. So I'm going to skip it for now. BF, I cannot draw it inside because it will create a crossing. So that one is forced, you see? And that's what I mean by the order. This I could actually use, but AE and BB I cannot use as my second one. So I cannot draw it inside. It's forced to go outside. And if I draw it like that, or if I draw it like this, it's kind of the same thing. Don't worry about it. It's like just like pulling, stretching that rubber band. So it's not, I'm just going to do like this because it's closer, but it doesn't matter. You're not losing anything. Then CE. I'm going to look at CE because that one, it's okay to look at it because it cannot be inside. It will create a crossing here with a V. So I draw it outside. Then CF, it cannot be inside because it will create a crossing. So I need to draw it outside. So I'm adding that one after. Mm-hmm. And again, this one I don't need the ordering in which I added the edges because it's plain. But it helps, It helps me actually find the drawing. So now I'm missing AE and BD. And as you can see, I can draw them inside and there's no problem. AE. Now it's forced, you see? In fact, if I try to draw it outside, it will create crossings. So now it is actually forced. Now that I have more restrictions, it's forced. And then BB, same thing. If I try to draw it outside, it will create problems. So it has to be like this. So this drawing not only solves my problem, but it's essentially unique because everything that I added was forced, except doing the upside, inside out. Everything that's outside could be inside and vice versa. But essentially, it's the only plain drawing of that graph. So here's the thing. So this is using the Hamiltonian cycle technique. But you could, if you want, and if you're lucky, or if you see something right away, like you see how this ones remain inside as they were before, and we just pull out the others. Well, if you see something like that, without actually using what I did here, the Hamiltonian cycle, if you just say, okay, I'm just going to pull this one out, that one, I'm just going to bring it out. This one, I'm just going to bring it out. And that one, I'm just going to bring it out. That's fine. That gives you a drawing. That's fine. Mm-hmm. And so in that first picture that I was starting in H24, so let me go to that one. Where is it? This one right here. In this picture, it looks like this. Yeah. So A, B, C, D, E. In that first picture, you can probably get away with it without having, without using the Hamiltonian circuit thing. You can just say, okay, I have this crossing, or, I have this in these crossings. I want to get rid of them, so I'm just going to pull that one out. I'm going to stretch that probably then. Mhm. Mhm. So I can stretch that one. So it goes like this, right? So this one right here, that one, I can stretch it so that it goes around, and I can also um, hmm, what else am I missing? Oh, this one. Now you can see that. What one? Am I missing something? Mhm. Um, um, let's see.
I think it's AE, right? The one that you're missing.
Yeah, but I'm missing some. Thank you, Elizabeth. Was it Elizabeth? I always
Yeah.
make up the voices. Sorry. Um, yeah, I'm also missing AE, but then I still have this crossing right here. You know, I still have this one right here. So let's see. So maybe maybe that one doesn't really work. Let me think. Mm, okay, well, uh, 1, 2, 3, 4. Any ideas? Anybody? Let's see.
I don't think it connects because of the crossing there.
Yeah, no, this one I don't think I will be able to finish this way, but it's definitely planar. This is not K5, so it's K5 minus 1h, right? So I can give you maybe just by pulling things, it will work. Uh-huh. But I can give you one, which is another example of things that you can do. This is K5 minus 1h, right? So here's one way of drawing K5 with less crossings. With only one crossing. Okay. You see that this is K5? Every vertex is joined to the others, but it only has one crossing. So this one is the same as, so the PE is the one that is not there, right? This is the only edge that is not in this to make it a K5. So that's going to be DE. And then I can label the other vertices in any way, and you can check that it's actually the same graph. A, B, C. Mhm.
Sorry, I'm a little confused here. Isn't K5 all degrees 4, or some degrees can be less than 4?
No. So this is not K5. This is K5 minus 1h. It's not K5. K5 is not planar. This one is. Huh? So for each of these problems, as long as you give me one representation, then you're good. One plane representation. I still want to do this by pulling something out. Anyways, I'll come back to this one, but this is one solution. This is one plane drawing. So if you recognize something like, for example, a K33, a K33 is not planar, but if you recognize something like a K33 that is missing one edge, then you'll know that it is planar, and then you can try to draw it with just that, with just one crossing, and then just remove one of the edges. There are many things that you can do, but all of these things that I'm saying are trial and error. Huh? The one thing that actually works all the time is the Hamiltonian circuit. So not all the time, but that's a technique that you can try applying most of the time. Okay. So, Elizabeth, what was the question that it was you, right, Elizabeth? The question that you had at the beginning that I told you we'll get to. We'll get to.
Yeah, what was the last one? 37 of by what do they mean by the error in trial?
Oh, the trial and error is the Hamiltonian circuit thing.
Oh,
So let's see. It's H37. So that this graph is non-planar by the trial and error method, starting with the Hamiltonian cycle. So that's exactly it. So you start by finding a Hamiltonian cycle. So you have this graph. This and this. Okay. So first thing you do here is find a Hamiltonian cycle. Hamiltonian cycle just means a cycle that passes through every single vertex exactly once. As if these vertices were cities that you're visiting, the edges are roads, and you wanna go, visit every single city once and come back to your original place. So here's one possibility. There may be others. There are others for sure. Okay? But there is a Hamiltonian cycle. I'm visiting every single vertex 1, 2, 3, 4, 5, 6, 7, 8, and back to where I started. And so that technique is the one where you say, label your vertices. I'm gonna label them in the order of my cycle because it's easier later. G, H, right? So then you start with that cycle, and if you want, you can just make a circle. And then just place the vertices in order. It doesn't matter if it's clockwise or counterclockwise.
Yeah.
A, B, C, D, E, F, G, and H. So this is your Hamiltonian circuit. And then you list all the edges that are missing. And then remember, you tell me in which order you add them so that each move is forced. So we're missing A, B. I usually go in order. If I label them with letters A, B, C, D, I go in alphabetical order. So A is only missing A, B. So I don't miss anything, right? And then B is missing B, E, and B, D. So B, E, and B, D.
And BG.
BG. Oh, thank you. Yes, B, B, E, B, D, and BG. Yes. So list everything that is missing. This one right here. And then C is missing CG and CH and CF. CG, CH, and CF. And then D is missing DA and DG. DA is already there because I went in alphabetical order. DB is already there. Same reason. So I'm missing DG. And then I go to E. EB is already there because we have GTP. We went in alphabetical order. EF. F is missing FC. Same reason, that's already there as a CF. G, I only have to check against the next letters, right? GH. So nothing. That's it. GH, HE is already there. So these are the edges that are missing. And then you can go in order, right? Remember, the first one that you add essentially can be anything. I try to start with almost a diameter. The further it's just what I try to do, but you can essentially start with any edge. I have a B, I can get started with that one. I can, but it doesn't really matter which edge you start with, and you can just assume it's in inside, and then you just number the edges. Eventually, because this one is not planar, you're going to get a contradiction. Right? But it's the same work that I was doing with that other drawing, but we didn't get a contradiction. In this one, you will get a contradiction. But remember to order, label your edges with the order you're adding them so that I make sure that every single step was forced so that you really are proving that it's not planar. Okay? That's what it means for part A. And then for part B, you need to find a subdivision, a K33 or K5. That's a subdivision. A K33 or a K5 or a subdivision of K33 or K55 in that graph. Mm-hmm. So, I don't know, my hint for that one is find a subdivision of K33. So when you find subdivisions of K33, you're looking for three, let's say, it's good to color your vertices, 3 red vertices and 3 blue vertices. All the blue are joined to the red, and you are allowed to use a few of the remaining vertices that are black in your graph as subdivisions of edges, right? But only one per edge. That's kind of the idea. So I don't know what else to say. Maybe what we can do is go to another example where you use, where you find a subdivision of K53. You want to do that? So we're here. So let's see. I think that the interesting graph was in some place. Or this one. Yeah. So like that one, for example. I can do, again, in this one, I'm going to find a subdivision of K33. And one reason why we're doing K33 and not K5 in this one is because K5 needs vertices of degree 4, and this one doesn't have vertices of degree 4. Okay? So they're saying, look for an appropriate subgraph to show that this graph is non-planar. It has to be K5 or a subdivision of K5, K33 or a subdivision of K33. It cannot be K5 or a subdivision of K5 because we will need vertices of degree 4, and there aren't any here. So we're going to find one of K33. So this is really trial and error. I'm just going to start by, I'm going to use that as one of my vertices. My red vertices, let's say. So I'm going to have 3 red vertices, and then I'm going to have 3 blue vertices. And every red needs to be joined adjacent to any blue, right? So I'm going to label this, I guess, A, B, C, and X, Y, Z. All right? So that's what I'm trying to look at in my graph with the only possibility of adding some green ones, right? Some subdivisions. So I'm going to do that one, red, and I'm going to start by and see if it works. I don't know if it's going to work, but I'm going to try making, the 3 that it is adjacent to, I'm going to try to make them blue. Maybe that won't work, but if it doesn't work, let's say that it doesn't work, then I can try making this, let's say, an edge. And so this one will be the blue one, and that will only be a subdivision. Remember that the subdivisions of the edges that I highlight are the ones, those that need to be degree 2, but within my graph, they can be other degrees. Okay, so I'm going to try those as blue. And then see if I can complete it. So each of the blue ones needs to be joined to red. So see, for example, if I look at if I look at this one, it needs to be joined to two other red ones. It's already joined. So let me just say that I'm using the, I'm highlighting this edge, and that edge. So this one needs to be joined to two other red ones. And right now it's actually joined to two vertices. So I'm gonna try this as red. So far I haven't used subdivisions and see if I can complete it. Sometimes it doesn't work, and again I have to adjust, but it's trial and error. We'll see. Okay, so now I need this blue one to be adjacent to these other red ones. It's not adjacent to those red ones, not directly. So I can try using paths instead of edges to join them. So I can use this, you see, and I can use this one as the edges that join from that blue to those two red ones. And so that means that I'm actually using these as subdivisions of edges. Okay, and now I need this blue one to join to be adjacent to these two red ones, and I'm not allowed to use any of the vertices that I have picked for something. So I'm only allowed to use this vertex and this vertex. Okay, so obviously it's not directly connected to those red ones, so I'm gonna use again some subdivisions. So I'm gonna go like this, you see? And that requires me to use this vertex as a subdivision of that yellow highlighted big edge. It's a path, really. And then I'm going to use this one. You see, I have to go from this vertex to that vertex. And the only way I can is going through this other vertex. So that's going to be my last edge. So this is my last edge. And this is another subdivision right there. But notice that each of the vertices that I'm using as subdivisions is only used for one edge. Like the ones that I circle yellow are in the yellow edges that are not really edges. They're paths sometimes too. And the ones that I circle green are only used for those green edges. So you can think of this as having, let's say, this is A. I really don't need the labels, but let's say that's A, and it needs to be joined to X, Y, and Z. So I'm gonna label those X, Y, and Z. Okay. And then X needs to be joined to A, B, and C. So I'm gonna label that one B and this one C. C needs to be joined to Z needs to be joined to B, A, B, and C. It's joined by blue here, and then by green there, and then by green there, which means that my HZB has a subdivision. So ZB. So if I were to make my graph here larger, what that means is that this edge, you see this edge right here, the Z, is actually a green one with a point here that I use as a subdivision. So let me call it S1. So that's what it is. Make sense? And then Z, oh, sorry, that was S1. It was supposed to be this one right here. That one right there, because it's Z to B. And the other one that was subdivided is from Z to C. So from Z to C, I also have these, green highlighted edge with another vertex someplace that's going to be S2. So this one is S2. You see? So you don't have to do all this. I'm just trying to show you how really we have, like the highlighted edges are actually making a subdivision of K33. The others that we have are Y to B. So Y to B is one of those highlighted yellow paths. See, that's like this one, Y to B. And I go through this vertex right here and then to B. So that's like having here vertex kind of in the middle. That's my S3, I'm going to call it. Like that's my subdivision 3. Makes sense? And then the other one that was subdivided is from Y to C. So from Y to C, I have that. I'm actually going through these other vertex. That's S4. I'm just labeling S4. So I guess I'll do it here. It doesn't matter where in the edge. So that's S4. And that's my other yellow edge. And all the other edges, like from A to X, Y, and Z, I just have blue edges, right? So from A to X to Y and to Z, I just have those blue edges. Yeah. So this one's right there. And then from B to X is also one of those blue edges. This one right there. And I'm missing C to X. C to X is another one of those blue edges. So C to X. It's just one of the blue edges. You see? So this vertex is like the S1 that I have here actually has degree 3 in my original graph, right? But in the graph, so in the graph of highlighted edges, which is the subgraph that I'm finding as the subdivision of K33, it only has degree 2. You see? Any questions? All right. Okay, so this requires practice. So hopefully, hopefully after trying a few problems, you get a little bit better. Let me know if you have questions. The quiz or homework/quiz isn't due until Saturday. Does it work for anybody? I usually have my weekend due dates on Saturday, but if you can do some extra day, I can also move it to Sunday. It's not a problem.
When is the quiz going to open?
Tomorrow morning. I have to set it open. Yeah.
Got it.
No, tomorrow morning. Mm-hmm.
Yeah, Sunday works better for me because I have tomorrow's my busy day as well.
All right. Okay, so I'll make it the quiz due Sunday so that I can upload the solutions on Monday. You can check them out, and if you have any questions, you can ask me on Tuesday. On Tuesday, we'll start section H in the combinatorics book.
Professor, when does the quiz open?
Tomorrow morning.
Okay, thank you.
Like for the subdivision problem that you just went over right now, like you said, it's pretty confusing. For me, the way that I view it is like you have 3 different color. You will use 3 different colors, and it's just for that one. It's just weird how you're labeling S1, S2, S3, 4. I'm still trying to like make sense of like why.
Yeah, take a closer look later. I just labeled them like that so that I can show you how this graph is actually that graph, right? The highlighted edges here make this graph. That's the reason I labeled them. But the labels don't really mean anything.
So is this graph, this graph a subdivision of this graph or something?
So this graph, so this is K33. This is a subdivision of K33.
Okay, because they look like the same graph between those two.
Exactly. So that's the idea that if you have something that looks like K33 inside your original graph, because K33 always has a crossing, then your original graph always has a crossing. So that's the idea. Because this looks exactly like K33, although it has a few extra vertices there, but it looks exactly like K33. Then this one will always have crossings, and this one is only part of that. We don't have these edges here. See this edge right here, this edge right here. We're not using those edges, so this graph is a little bit bigger than this one. If this one requires crossings, this one requires crossing, and this one requires crossings for sure because it actually has more edges. So that's the idea. When we look for the subdivision, we don't need to use all of the edges. We're only using part of them so that we can actually find a copy that really is almost the same as K33. Okay?
Professor, you are writing here K33, subdivision of K33, and another one is it what?
Oh, this is a graph containing K33. A graph containing this subdivision, a subdivision of K33.
So if you were to give us this graph and told us to find a subdivision that is non-planar, which means allows for crossing, or we need to create a graph that does crossing.
No. So if I ask you to prove that something is non-planar, if you're using technique 3, you need to find a subdivision inside it.
Professor, what is S1, S2, S3?
Those are vertices of my original graph, and I just label them so that you can make the connection between these two. You see, this one has 6 vertices. This one has 10 vertices. I added 4 more vertices. Okay? This one has 6 vertices. This one has 10 vertices. Because I added the S1, S2, S3, S4. So they're almost the same, right? This one has 9 edges. This one has 13 edges. Because here this is actually 2 edges. 1, 2, 1, 2, 1, 2, and 1, 2. So this one has 13 edges. This one has 10 vertices and 15 edges. You see, I made it even larger. I started with that one, I added a few vertices, and then I added those edges.
My question is generally the subdivision should be the smaller than the original one.
Exactly. So we keep going, right? So
this is my point. But my question is, if my original one is K33, then subdivision of K33 will be
just itself.
It will be less vertices and less edges. This is my opinion.
No, if you start with K33, you say it's not planar because it's K33. We already know that K33 is not planar. So you wouldn't really start from K33. You can think of K33 is itself, K33.
But when it is subdivision of K33,
I wouldn't ask you to find a subdivision of K33 in K33. Okay? All right, guys. I have to go, but I'll be in my office hours at 2. You are very welcome to come, and we can continue discussing subdivisions or whatever other questions you have on the homework, okay?
Okay,
Thank you.